Okay, so the fourth problem is this one with the two carts. Here they are with their initial velocities, and then they hit each other, and the spring compresses. Okay, so then the spring compresses, and then they finally lose contact with each other. Sorry, I'm over to right. Spring gets fully extended again at the end, and will eventually have to find their final velocities, so v1 and v2. Okay, so pardon my even worse than usual drawing, and boy, that's saying something, isn't it? So the first question A is, when the spring reaches its maximum compression, which is right here, what are the velocities of carts 1 and 2? So this requires a little bit of sort of lateral thinking, or looking at the grand picture. What I'm trying to get to you guys is the idea of looking at a system and talking about the property of the system instead of just the properties of the individual objects. So we're going to treat the two carts as a system. We're going to draw so I'm going to just draw it on the first one. We're going to draw a dotted line around the things, and the carts and the spring, of course, are all part of the system. So the question I want to ask is, and here's the system boundary there. The question I want to ask is, are there any net external forces acting on the system? And if you think about it for a moment, you realize the answer is no, because the normal force from the ground and gravity cancel each other out. So the only other forces on the carts are are the forces the spring exerts. And here, in this first case, the spring exerts no force on anything because it's not stretched, right? Or it's not extended, it's not compressed. Here, the spring exerts a force on cart 1 in that direction, right? And exerts a force on cart 2 in that direction. Well, those add up to 0, which, when you think about it for a moment, is sort of an obvious conclusion because, Newton's third law. It's an internal force. Equal and opposite cancel out, okay? And so finally, you also have 0 spring force there, obviously. So the point is, this system is isolated. So there are, and this is so important, I'm going to write it in this lovely shade of pinkish purple. I guess it is pink. All right. No net external forces. Okay, so what that means then is we can talk a little bit about properties of the system that stay what can I say, values, numbers that remain constant because of the lack of external forces. So if you haven't really made much attempt to solve this problem, but you want a hint, I would say right here is where you should stop for a moment and try a little more to do the problem yourself. Think about what it means, and if you really are stuck for a while, then come back and I'll give you another little dollop of information. Okay, so pausing for you to stop and. Okay, so now if you're listening here, you must have come back for more. All right, so when the spring reaches its maximum compression, what are the velocities of carts 1 and 2? Well, that's this picture here, the middle one, and what we know here is that these must have the same velocity, right? Because this is the point where the spring reaches its maximum compression, and so max compression, and which means the distance between these two guys is at its shortest. Okay, so at that moment, the distance between them is not changing, which means they must have the same velocity, right? So whatever the velocity of 1 is here is the same as the velocity of 2. Okay, that's going to be the case, and that's another little hint that maybe you should keep trying to solve it on your own. Now that you have that, think about that. Think about what that means. Okay, Okay, so now the key fact that works in our favor here is that when there are no net external forces and I'm just going to do this in pink, in this hot pink color. Okay, so with no net external forces, what does that mean? Well, remember that the sum of external forces on a system is going to equal the total mass of the system times the acceleration of its center of mass. Okay? So, what does this mean? Well, if there's no net external forces, then this is 0, okay? And total mass of the system obviously is not 0. In fact, we know exactly what it is. It's m. So that's going to be, 0 is the mass times the acceleration of center of mass, which then shows us pretty clearly that the acceleration of the center of mass, and I'm going to switch to scalars because this is a scalar situation, 1D. The center of mass is not accelerating. Okay? What that means now is that the center of the mass must be, the velocity of the center of mass, what did I just say? Oh, anyway. Velocity of the center of mass must be constant. Okay? Try to do the problem yourself from here on. Blah, 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 blah. Okay. So, the velocity of the center of mass must be constant. So in all three of these, this one, this one, this one, you must have the same velocity for the center of mass. And if you think about it with this middle one, which is the one we care about right now, for part A, you have both halves of the system moving at the same velocity. So if every part of a system is moving at the same velocity, then doesn't it stand to reason that the center of mass of the system is also moving at the same velocity? Right. So the answer for part A is that both carts, when the spring reaches maximum compression, both are moving at velocity of the center of mass. And if you really want to find what that is, that's not very hard. You say velocity of the center of mass, VCM, is P total momentum over total mass, which is equal to, that's going to be the mass of 1, which is m over 2, times u1 plus m over 2 times u2 all over m. And so pretty obviously this is just going to be the linear average of u1 and u2. So VCM, which equals 1/2 of u1 plus u2. So I'm going to close this video here, and I'll do part B in the next video.